Hey, it's Mr. Stellatano, and this video is going to be on electromagnetic waves. So the waves that you see here, all of these waves that you've heard of before, are going to be what we're describing and really how they behave and how we get them. So for all the way from gamma rays to X-rays we've heard of, to ultraviolet light, to colors, to infrared waves, to microwaves, all the way to radio waves. So this is the whole spectrum that we're covering in this video. So the reason why we're covering this is because we know a lot more about the atom based on these electromagnetic waves, based on this electromagnetic spectrum. There are some things that all of these waves have in common though, whether it's a microwave or a gamma ray or an X-ray, some things they all have in common. The first thing is that they all consist of electromagnetic waves. So light in general consists of electromagnetic waves, and what that means is this light has electric properties and magnetic properties. So that's what it means if it's electromagnetic. Electromagnetic waves also travel through empty space, so they don't have to have anything there for them to travel. That's how the sunlight gets all the way to the Earth, because if you look in the image, the light and all the other light waves that we're going to be talking about get to the Earth because even though there's nothing in space to travel through, they don't need anything to travel through. So that makes electromagnetic waves unique compared to some other waves. They also transfer energy, so that's one of the things that all these waves do. It's what makes them electromagnetic waves, is that they transfer energy. And finally, they travel at the speed of light. So all these different types of waves we're looking at travel at the speed of light, which is actually around 300 million meters per second. So that's extremely fast. So just first thing, these electromagnetic waves are different from sound waves, for example, because sound waves actually you have to have air present to hear. So that's why, for example, they say in space no one can hear you scream, because in space there's no air to actually carry your sound. So without any air there to carry your sound, if you were to try to talk to somebody in space, it would never get to them. That's why we actually use radio waves, because radio waves can travel through empty space, which is an example of an electromagnetic wave, which is, again, the whole point of what we're talking about here. Something else interesting about light waves versus sound waves is, if anybody's ever run track before, the reason why they use the gun to start the race rather than using a whistle is because the timer, especially if they're far away, they're supposed to be looking at the smoke of the gun and not so much the sound of the gun. And the reason is because light travels much faster than sound, right? So electromagnetic waves travel at the speed of light, and you can actually see the gun smoke a lot of times before you even hear the gunfire because the light travels so much faster. So if you want an accurate time of the actual race, then you need to use the gun smoke and not just the sound of the gun. So that's why we do that. So seeing the smoke itself, that light is traveling because it's electromagnetic at the speed of light. Sound waves are very, very different from the waves we're talking about. So the electromagnetic waves in some ways behave just like other waves you can think of. That's why we call them waves. And in some ways they look just like ocean waves, for example. So some important terminology we need to have about these waves. We need to know the parts of them, basically. The first thing we want to know is the wavelength, and that's considered the distance technically from crest to crest. So here is the crest of a wave, which is the top, like the crown, the crest. And here is another crest. And then, so the distance between those is the wavelength, and that actually varies from wave to wave, and that's why it's so important that we can measure that wavelength. The letter for the wavelength is the Greek letter lambda, so that's what this means. This funky looking thing here is the Greek letter lambda. Another very important property of waves is the frequency. So this is considered the number of waves per unit time. And the way that we measure that is a very strange unit. It's called the per second, so seconds to the -1, which is also called the hertz. So for example, this wave down here has a much higher frequency. So this is actually, you're going to see a lot more crests of this wave per second. You see it has a lot more hertz to it. A lot more waves travel through a certain amount of space per second than in a low wave frequency. So this is a low frequency over here, so imagine this wave is in motion. By the time we get from this to that wave to the next wave, the frequency is a lot lower than this, which has a high frequency. Look how many more waves we have just in this short segment here. And again, it's very important that you know that unit. We measure frequency in hertz, which is also thought of as per second. And again, we want to look at the crest. The crest is just the top of the wave. So here's the crest on the longer wave. Here's the crest on the short wave. And then we want to look at the amplitude. So that's just the distance from what's called the origin here, which cuts right down the middle of the wave horizontally. So the amplitude is the distance from the origin to the crest. And the origin is just the line that cuts through the middle of the wave. It's like equal distance from the crest to the bottom, which is called the trough. So the bottom of the wave is actually called the trough. The top is called the crest. And you can see a very big difference here. This has a short wavelength on this wave. This has a longer wavelength. This has a high frequency. There's a lot more waves here for the same section. And this is a lower frequency. There are much fewer waves passing per given amount of time. And so again, that frequency is in hertz. So a lot more hertz here, a lot fewer hertz there. And like we said, the crest is the crown. Okay, so the electromagnetic spectrum, so these are all these waves all the way from gamma over here to radio waves. And this whole thing is what we want to be able to use. You're not going to have to memorize all of them, but you want to know the general properties that we're talking about. And these are all included in the electromagnetic spectrum. So at this end over here, the gamma rays, they're thought of as having high energy because they have a high frequency and they also have a short wavelength. So just like, they're more like this bottom one over here that we were looking at. That's much more like gammas. That's the one extreme. And then if we look at radio waves on the other extreme, they're the complete opposite. So they have low energy. Now you want to think of the three L's. They have low energy because they have low frequency and they have a long wavelength. So LLL, low energy, low frequency, long wavelength. They're a lot more like this one here. So we have a long wavelength, a low frequency, and low energy. So that's what radio waves are like. Now the rest of the waves fall somewhere in between those two extremes, and that's what makes them act the way they do. And this is just kind of a comparative thing to the size. So gamma rays all the way down to the size of maybe the nucleus of the atom, and then as we grow, we actually see the different types of waves are actually much longer in wavelength until we get to things like the atom, to an actual molecule, to very, very small species, to buttons, to bees, to humans, and then wavelengths of radio are supposed to be as big as a building, for example. So that's the extreme difference between these wavelengths for these particular different types of the electromagnetic spectrum. Now, which is more powerful, a lot of ocean waves at a time or a few ocean waves at a time? Well, a lot at a time, right? And so that's why those high frequency waves, like the gamma are the highest frequency on the electromagnetic spectrum, they have a lot more energy because they're hitting a lot more in a given amount of time compared to the low frequency waves. So let's start by looking at gamma. So gamma rays have the highest frequency, so they have the most energy, right? We looked at, they have the shortest wavelength as well. So all those three things happen. And because of that, they're the most penetrating, and so they travel through most solids. So they're going to travel through your paper, through your wood, and through. It would actually take a few meters of concrete to stop them, or a few centimeters of lead to stop gamma rays. So gamma rays have the most energy essentially, and they penetrate the most because of that. Now, when you get to X-rays, they have a slightly lower frequency. There aren't as many waves per unit time in X-rays, and their wavelength is also a little bit longer, and so they actually just penetrate to the bone, right? And that's how we see our bones from X-rays. So not as penetrating as gamma rays because of those things. And then if we go over to the ultraviolet light, that's what gives us our sunburn, right? That will penetrate to the skin. So that's easier to think of. And again, it's not as penetrating as the other ones because the energy goes down as we go across the spectrum. Gamma rays have the most energy because they have the highest frequency, right? There's the most per second, and they have a short wavelength. As we go across, the wavelength gets longer, and so the frequency gets lower, and there's less energy, those three L's again. That's important. The visible spectrum, here's what's interesting. So all of these other parts of the electromagnetic spectrum obviously exist, but you cannot see them with your naked eye, right? But the visible spectrum is still part of this. It's still part of the light we're looking at, but you can see it with your eyes. That's why they call it the visible spectrum. But what you may not have known is that there are still differences in wavelength and frequency and energy, and that's what makes us see these different colors. So for example, red, what would the wavelength be like in red compared to the other colors? Well, the red has a longer wavelength. And so what would the frequency be like? Well, it's a very low frequency, right? And so the energy would be lower as well. If we go to the other extreme, the violet, so the violet has a lot shorter of a wavelength. And that's what makes us be able to see it as violet. The violet also has a higher frequency, right? There's a lot more waves here than there are at the top, so the frequency is higher. And the violet's going to have a higher energy as well. So that's why we can see red this way, the other colors we can see based on their wavelength. And it's usually measured in nanometers, so very, very tiny, but it still makes a difference in what we can actually see with our eyes. Our eyes pick these up differently. And so violet is much different than a red. Now, just a little bit of where these names come from. So if you look, actually, the extreme end of the visible spectrum, so this rainbow is the visible part of the electromagnetic spectrum. The extreme end is the violet end on the left, and so that's why we have ultraviolet, UV, that's just before the violet. But if we go to the other extreme next to the red, that's infrared. So that's where part of the place where these names come from is because the wavelength is just next to either violet or the red in the visible spectrum. So just kind of interesting and fun fact. Something else you might find interesting is that even though we only see the visible part of the spectrum, other species might be able to see different parts of the spectrum. So for example, on the left, if you look at this flower, that's how you would see this flower in real life. This is the visible spectrum seeing this flower. But if you're a bee and you can see the UV spectrum, you can see the ultraviolet, the flower looks very different to you. Here's the flower off to the bee. And so that's important for nature because the bee actually can hone in on where the nectar is. The bee is looking around at all these flowers, and instead of seeing a bunch of yellows, the bee is like, ooh, red, that's where my nectar is going to be. And so that's going to be important for them to be able to find this. So again, light is comprised of this whole spectrum. It's just that this is the only part that we can see. But the other parts are very much there and are just as important. Okay, so a little bit of review. So label the parts. So what part would be labeled A? What part of the wave is labeled A? That is the crest, right? The crown of the wave, the top. B is going to be the trough. So we talked a little bit about the trough. What was C again? Going from the origin to the crest, what was that called? The amplitude. So the height of the wave from that point. And then, most importantly almost, D, what would part D be? That would be the wavelength, right? The length from crest to crest, which differs significantly from wave to wave. So there's something else that you want to know about the waves too besides these parts, and that's that if the waves have a long wavelength, that means they're going to have a low frequency and low energy. So the 3 L's, long wavelength equals low frequency equals low energy. And you want to know that, for example, that would be radio, and the opposite end is gamma. So those are the things you want to remember. Thank you for watching, and remember, chemistry is everywhere.